let's start off with the internal capacitive effects in the MOSFET, and let's try to derive the high frequency model of the MOSFET. Okay, so BJT we will not be doing for now. We don't need it as it's not there in our current syllabus. So I was telling you yesterday the structure and construction of MOSFET. As you can see here, yeah, you can clearly see this. I told you there are two N plus regions embedded into the P-type substrate. So at any point of time, there will be two PN junctions formed between this source and the substrate, drain and the substrate. And wherever there is a PN junction, we know there will be some form of depletion layer. And whenever a depletion layer is formed in a PN junction, it will act like a parallel plate capacitor. Remember, a depletion layer is what? One type of immobile carriers. Say I have positive immobile carriers on the N side and negative immobile carriers on the P side. So it will be a collection of charges on two sides with a small gap in between, separated, and that is acting like a parallel plate capacitor. So there will always be some capacitance developed whenever there is a PN junction and a depletion layer formed in the PN junction. So please remember, the source and the substrate has one PN junction, and this drain and substrate will have another PN junction, and both PN junctions will act like parallel plate capacitors. I was telling you, because immobile carriers will be collected. So immobile carriers are collected on either side of the N and P type, and because of that there will always be collection of charges on two ends or capacitive effects. So you can expect one source to substrate capacitance or source to body capacitance, we call it as CSB. One drain to body capacitance, we'll call it as CDB. And from the gate alone, see this gate, the metallic or polysilicon material which is put on the oxide layer. This dashed line here is the oxide layer, the SiO2, silicon dioxide layer, and below that the channel will be formed. Due to this gate alone, there will be three more additional capacitances. So in fact, we will have totally 5 capacitances or 5 additional capacitive effects which will induce themselves in the behavior of the MOSFET. So the effect of all these capacitances, I was trying to explain to you yesterday, is to slow down the response. The response time of the MOSFET will be very slow. I was telling you, especially consider that time when there is a very sudden change in the input, like a square wave. I'm not able to draw a proper square wave here. So when there is a sudden jump in the input, the output cannot respond as quick as that sudden change, but it will take its own time. So for it to reach this level, it will take a larger time. You can see this time gap between change in input and the change in output. And that is caused mainly because of these device capacitances. And please note, these device capacitances will, they will not have any effect at low or mid frequencies. So all these device capacitances will have effect only at high frequencies operation. Why so? Why it has effect only at high frequencies? For the simple reason that whenever frequency is high, it means the time period is small. So time will be very small whenever frequency is high. That means the input changes very fast. The changes in the input occur very fast, or the time duration, time gap between the changes in the input will be very, very small. Very low time, the input changes very quickly. So the output also has to respond as fast as the input changing, and that is the biggest problem, because the capacitances will not allow the device to respond so quickly. So all these capacitances will come into effect, or they have to be considered for high frequency operation. So low and mid frequencies, we need not worry about these device capacitances or the internal capacitances. But at high frequencies, we surely have to consider them. And after considering them, we derive the high frequency equivalent model for the MOSFET. So please remember, for the MOSFET, we write a low frequency equivalent model that will work for low and middle frequencies. And for high frequency, we write a separate model. So I was telling you the two main capacitive effects are the gate capacitive effect, which is due to this gate alone, which can either be formed with a metallic or polysilicon plate on top and the channel below. And there is an oxide layer, silicon dioxide layer in between, as you can see here. Here, metal, silicon oxide, channel will be formed here. And the source body, as I told you, between the source and the body, there will be one capacitance because of the PN junction depletion region. Between the drain and body, there will be another capacitance. So all these capacitances will come into effect, as we will see. So as I was telling you, three capacitances due to the gate alone: CGS, gate to source capacitance; CGD, gate to drain capacitance; and CGB, gate to body or gate to substrate capacitances. Three due to the gate terminal alone, and CSB stands for source to body capacitance. CDB is drain to body capacitance. Let's see the gate capacitive effect first. So this gate capacitive effect can be modeled by three different capacitances. As I told you, CGS is the main there. Then we have CGD and CGB. So we'll have three different capacitances to model this gate capacitance effect. You can see here, I'm showing you the characteristics of the MOSFET. Please remember, we had three regions of operation. Triode region, this region. So triode region, as you can see here, this is that triode region. Then this whole thing is the saturation region, and the region below this line, this region is the cutoff region. So in the three regions of operation, the value of these capacitances will be different. So we are talking about internal capacitances which will develop inside a MOSFET. And what would be their values in the three different regions of operation? Let's see. And okay. So first, when the MOSFET is in the triode region. When it is in the triode region, remember, this drain source voltage is very, very small. So VDS, this x-axis or the drain source voltage will be very small whenever the MOSFET is in the triode region. And the channel will be having uniform depth. Remember, we have a channel formed here. You remember this channel. The channel which will be formed below this gate region will be uniformly distributed, equal in length. Okay. So it will be uniformly distributed. So what happens now? The gate channel capacitance will be of value. You see W is the width. You see this is the width. Can you see here? The width of the channel here. Usually we are considering the channel below the gate region which will be formed. So W stands for the width of the channel. It will be inside like this. L is the length of the channel formed, and Cox is the capacitance developed under this gate between this metallic gate plate and the channel. I told you, remember, it acts like parallel plate because of this oxide layer. We'll call Cox as the oxide layer capacitance in farads per unit area or something like that. So we call that as Cox per unit area, per meter square. Okay. So total value of capacitance developed in this region will be W into L into Cox. Cox is the capacitance per unit area. So you can see the total capacitance will be, when the total capacitance is WL into Cox, we have two regions. One part of the capacitance is between what? The gate and the source. and another part will be between gate and drain. So we'll divide it into half. This is just an approximation. So don't worry about this. You just remember CGS and CGD will be half WLCox in the triode region. So gate to source and gate to drain capacitances. Okay. And this is the total capacitance we consider as WLCox because we have considered two separate values. One is due to gate and source, one is from gate to drain. We'll just divide it into half and consider this. Anyway, this will not be used in our model because we are not going to operate the device in the triode region. Remember, triode region is used only in some special purpose applications. In almost all applications which we deal with, our amplifiers, we'll normally be working in the saturation region. Okay. So we'll not be working in the triode region. So this is just the triode region capacitance. Next, we'll move on to the operation in saturation. When the device is in saturation, remember, how will the channel look? It will be maximum, it will be having maximum width in one side and it will get pinched off in the towards the drain. When does it get pinched off? As and when the drain voltage increases. Remember, as we increase the VDD or VDS, the drain to source voltage, the channel becomes narrower and narrower and it gets pinched off at some point. So the channel width will not be uniform. In the previous case, this channel would have been uniform like this. Okay. But now it is not uniform. It will be having different widths and it will look like this in the saturation region. So it can be shown, it's a complicated derivation which is out of the scope for you. So in this case, it is proved that the value of the channel capacitance will be approximately 2/3 times WL into Cox. In the previous case, it was half WL Cox. Now it is 2/3 WL Cox, the gate to source capacitance. Remember, gate to source means it will be towards this side. Here, the width of the channel is maximum, so there is a capacitive effect present. But look at the region towards the drain. The width of the channel is 0. It's almost like the channel is completely pinched off. So there won't be any capacitive effect. That parallel plate effect will not be there. You remember the gate metal will be there on top and the channel is down. So if the channel is there, then there is a parallel plate. If the channel is not at all there here, it's completely pinched off, then towards the drain end, the capacitance will be 0. So you see, you have to remember this. The gate to source capacitance will be 2/3 WL into Cox, whereas the gate to drain capacitance will be 0 in the saturation region. So in the saturation region, we will be using the device and this is the value of CGS and CGD. Anyway, though it is 0 here, in the next analysis we'll show CGD will also have some value. Okay, please remember this. Now, third point, there is another additional capacitance which appears due to the gate, and this happens when the MOSFET is cut off. Remember, cut off means the device is completely in switched off mode. In the sense, whatever VDS or VDD you apply, there is no current flowing. So when the device is in cut off, so the gate voltage is less than threshold, it will remain in cut off. Both the gate to source and gate to drain capacitance will be 0. But however, there will be some small effect due to the gate and substrate terminal. So between the gate and substrate terminal, there is a small capacitive effect which can be modeled as WL into Cox. So everywhere it is the same WL into Cox. In the triode region, it is half WL Cox. In the saturation region, CGS is 2/3 WL Cox, where CGD is 0. Whereas in the cutoff region. Here we are thinking of cutoff region of the characteristics when the device is off. Gate voltage is less than threshold. Then CGS and CGD are both 0. These are the important capacitances for us. But gate to body, one small capacitance, all these values are very, very small. They will be in the range of femto and picofarads, as you will see in the example. Okay. So this would be the value WL into Cox. Now there is a fourth capacitive effect because of the gate, and that is known as overlap capacitance. What is this overlap capacitance? You can see in this diagram. Yeah, can you see here? There is always a small overlap of the gate on the source as well as on the drain. Can you see the oxide and metallic layer? A small overlap is there in this end as well as this end. That overlap length will be, we call the length of overlap. Okay. Here, if I try to measure it, this overlap at this end is so much. At this end, the overlap is so much. I'll call that length of overlap as LOV. Okay. The length of overlap is known as LOV, and that overlap causes a small capacitance effect. Okay. And that is known as the overlap capacitance. So the value of this overlap capacitance can be added to the gate to source capacitance as well as gate to drain capacitance. See why? It exists on both sides. The overlap is there between gate and source. The overlap is also there between gate and drain. So you can clearly see that the overlap exists on both sides, and whatever capacitance effect is created due to that will be added to both CGS, gate to source, as well as CGD, gate to drain capacitance. And how do I find that overlap capacitance? I call it as COV. It is also measured as WL into Cox. Here the L which I should use is not the channel length. Previously, this L indicated the length of the channel formed, whereas now it is the length of the overlap region. What length of the channel overlaps, that we have to see. It is usually a small value, okay, 0.05 to 0.1 of L. It will be 5 to 10% of the actual length of the channel, as I showed you. So this overlap capacitance, as I told you, please remember, gets added to the gate to source as well as gate to drain capacitance. So let us see next the junction capacitances, which happens between. So till now what we saw was the gate capacitive effect. So as I was telling you, the gate capacitive effect caused CGS, CGD in the triode, saturation and cutoff regions as we analyzed, and it also caused an overlap capacitance COV. Okay, this is all due to the gate region. Next we'll see the junction capacitances between source and body terminals and the drain and body terminals. As I told you, you can read here, two reverse biased PN junctions are formed between the source and drain as well as source and body as well as drain and body, or the body is nothing but the substrate terminal. And I don't know whether in ED you have derived this, but now the derivation is not in our scope. You just have to remember the relation. The source to body capacitance is measured as the value of the source to body capacitance when there is zero reverse bias voltage. Remember, the source and body are always reverse biased. If the source is N plus type, the body will be P type. So the junction, we always, please remember, in any circuit, the substrate or the body is kept as at the most negative potential. Whether it is used in ICs or any circuit, the body terminal is at the most negative potential in any circuit. So always remember, source to body as well as drain to body will always be in reverse bias. So there will always be a reverse bias depletion layer between source and body terminal, which causes this capacitance. So how do we find this capacitance? The value of capacitance when there is zero reverse bias voltage between the source and body divided by root of 1 plus what is the actual source to body voltage which we are going to apply. VSB stands for the applied source to body reverse bias voltage, and V0 represents the voltage of the junction, which is normally in between 0.6 to 0.8 volts. So CSB is measured like this. Similarly, so as I told you, SBO is the value of C capacitance at zero body source bias. VSB is the amount of reverse bias applied. V0 is the junction built-in voltage, 0.6 to 0.8. Similar to this, we have CDV. Both are similar. You can look at both the equations. It's easy to remember. Both are similar in derivation. So this also is CDBO or CDB0. So the value of the drain to body capacitance at zero reverse bias between them divided by root of 1 plus voltage, which is the reverse bias voltage applied between drain and body divided by the junction built-in voltage V0. Okay, so both are calculated like this, and here in the derivation they actually use an M grading coefficient which is considered as half. Anyway, you don't need that, you just need to remember these two equations. So finally we have defined 5 capacitances coming into picture. So we can consider a problem and its solution. As you can observe here, for an N-channel MOSFET, TOX 10 nanometer, L 1 micrometer, the same values are listed here, you can see. W 10 micrometer, the length of overlap of the channel and gate is 0.05 micrometer. And the basic values of source to body capacitance at 0 volts, drain to body capacitance at 0 volts, 10 femtofarads, and the junction voltage 0.6 volts. I told you it will be in the range 0.6 to 0.8. And the source to body reverse bias voltage is 1 volt and drain to source voltage is 2 volts. Please note, they have used drain to source voltage just to confuse you. Now, there are ways in which we can measure COX. This is actually mentioned in the beginning. So the oxide layer capacitance is always computed as the permittivity of the oxide layer, epsilon ox. Epsilon stands for the permittivity of the oxide layer divided by the TOX. So TOX, as I told you, is the what do you say? The width of the oxide layer, or the duration, the length of the oxide layer. Okay. So epsilon, actually you remember capacitance is found as epsilon A by D. So this D stands for the distance or the length, and A area we are using 1 per unit area. So the oxide layer capacitance is calculated as epsilon A by D, or in this case it becomes epsilon into 1 divided by, here D is given as the value TOX. Okay, 10 nanometer. And how do I find this oxide layer capacitance for silicon dioxide? For silicon dioxide, it is 3.9 times the permittivity of free space, epsilon naught. We know epsilon naught represents the permittivity of free space, which is 8.854 into 10 to the power of minus 12 farads. And 3.9 times epsilon naught will give you the silicon dioxide capacitance. So using that formula, you will get the oxide layer capacitance as 3.45 millifarad per meter square. Okay. So if you find COX, the all other capacitance depends on COX. So now I can find the overlap capacitance COV. Remember that overlap regions, the length of overlap LOV is given as 0.05 micrometers here. So COV is measured as WL into COX. So the width is given as 10 micrometer, LOV is 0.05 micrometer, and COX we have computed 3.45 millifarad per meter square. So the overlap capacitance is 1.725 femtofarads. Femto is 10 to the power of minus 15. I hope all of you remember it. Next is the gate to source capacitance. Remember, just observe in the problem they are asking us to calculate all these capacitances when the device is operating in saturation region. So we have to remember the gate to source capacitance in the saturation region will include the basic 2/3 WL COX which we had defined. In saturation, this was the value. Remember here, CGS in the saturation region, because here the channel existed, is 2/3 WL COX, and CGD is 0 in saturation. But to that, what else should I add? I should add this overlap capacitance. This overlap capacitance exists in the saturation region only. So what we are doing, I am adding 2/3 WL COX plus WLOV COX. That is nothing but our COV. We have already computed this. So you just need to compute 2/3. W is the width of the channel, 10 micrometer. L is the length of the channel, 1 micrometer. And COX, we have already computed, oxide layer capacitance, 3.45 millifarad, plus COV, which is 1.725. This value is nothing but COV. So I'll get, you see, this is a considerably large value. When compared to COV, CGS is surely larger. It is 24.725 femtofarad. Okay. So we have computed, please remember to do this. In the saturation region, the value of CGS will not be just 2/3 WL COX, but to that we should add this COV also, the overlap capacitance. CGD, if I compute in saturation, ideally CGD was 0. We saw because the drain end, the channel was pinched off. But because we have to add the overlap capacitance to that, it is 0 plus WLOV COV, which is 1.725 femtofarad, already computed. Finally, we have to find the capacitance between the source and substrate, CSB. CSBO divided by 1 root of 1 plus VSB by V0. CSBO is given as 10 femtofarad, as you can see. V0 is 0.6 volts, VSB is 1 volt. This is the actual reverse bias. So substituting all that, I'll get CSB as 6.123 femtofarad, and CDB, the drain to body capacitance, in the same value, in the same way when we calculate. Here, the drain to source voltage is given. I was telling you in the beginning, take care. But what do I need here? I need the drain to body voltage. How will I calculate that? I have VSB and VDS. So how can I find, how can I find this VDB? VDB is, I can say, VDS, just add, plus VSB. So VDS plus VSB, if I add, the overall effect will be VDB, correct? VDS plus VSB gives you VDB. So 2 plus 1 volt, it will effectively become 3 volts. We'll get this as 3 volts, okay? So that's why I have used 3/0.6 and you'll get this value. Any doubts with this? Hope you're following. So this is about the device capacitance effects and the related problems. So let's move on. With this knowledge, let's try to write the high frequency model of the MOSFET. So please remember, all these capacitances will have a significant effect only at high frequencies. At low and mid frequencies, you need not bother. You need not worry about the effect of all these. Only at high frequencies, you should consider all these things coming into effect. And the equivalent model looks something like this. So you have the gate terminal, the drain terminal, the source terminal, and the substrate or body terminal. So in our original model, between the gate and source, it was an infinite resistance. We did not have anything in the previous hybrid pi model which we used to write, right? But now there is a gate to source device capacitances coming into picture. So there is a device capacitance CGS coming into picture, and that comes between the gate and source terminal, and between the gate and drain terminal. Remember, in our original hybrid pi model, there was no connection, but in this model, in the high frequency model, there is a capacitive effect between the gate and drain terminals, and that is called CGD. The gate to drain capacitance should be written. And in our previous model, we have this dependent current source, GMVGS, and only this we have. Here we have an additional dependent source because of the body and the source terminals. So between the body and source, there is a voltage. So if the body and source are not connected together, if these two are not shorted, S and B are different, so between them, whatever voltage is there, that will lead to a small current flow. So there is a very small current flow due to minority carriers. Please remember, they are reverse biased. The source and body are always in reverse bias. And even if it is reverse bias, there is a very small current flowing in that reverse bias junction, which will give you another dependent current source in this region. And that dependent current source is GMB VBS, as you can see here. That is because of the source and body being separate, and the voltage between them in reverse bias, which causes minority carriers to flow and a current of value GMB VBS. Though it is very small, it will have some effect here. Okay. And R0 we had in our previous model also. The output impedance R0 we had, and we had only this source. There is an additional source and 4 additional capacitances to consider. You can see CSB between the source and the body, CDB between the drain and the body. So this is our actual high frequency model of the MOSFET. But I think as you will see this model is too complicated and too big for analysis. So normally what we do, we'll try to simplify this model. So let's try to simplify this model. The best way or easiest way to simplify this model is to short the source and the substrate terminals. So if you short the source and substrate terminals, I'll show you the simplified model in the next case. You see here, this was our original model. So for manual analysis and working, we need to do manual. We are not using programs or SPICE models to analyze. If you use SPICE models, you can use this original high frequency model with all these things. But for manual analysis, this would turn out to be very complicated. We'll simplify the model. So the first step in simplifying is to short the source to the body terminal. So in this case, you can see in this diagram, the source and body terminals. Okay. So the source and body has been shorted together, and look at what happens, which are the capacitances which goes off. Naturally, the source to body capacitance will not be there because now both are the same terminal. So when both are same terminal, there is no voltage difference between the source and the substrate, correct? When there is no voltage difference, there is no capacitance. This CSB is removed. You can see here, CSB is not there. The other capacitances, this CGS, CGD, this current source is there. And why this current source is absent now? You see this GMB VBS, the body to source current will not flow because both are at the same potential. the source and body are at the same potential. There is no reverse bias between them. So naturally, there is no flow of minority carriers, no current source. You need not consider this current source. Okay. So this capacitance is absent, this current source is absent, and R naught is there as usual, and this CDB will be there. It is now between, so the B and S are the same terminal, so CDB is between drain and the source now. You can also call it CDS. Whether I call it CDS or CDB, it's one and the same because S and B are common. So this is our equivalent simplified model. Now we can simplify this a little more further. Okay, so somebody is making, okay, we can simplify this one more step further. As you can see here, this is simplified. What have we done here? We have removed this CDB because it is very, very small and it won't have any significant effect on the circuit behavior. So the drain to body capacitance is very small. So we have removed it from the circuit. The rest of the circuit is there as it is. So don't you think this is quite simple now? This is a very simple model which can be used for our further analysis. So this is our high frequency MOSFET model.